Hey everybody, what's happening? Today we're going to go ahead and learn about the age of the Earth. And it's pretty old, so go ahead and make sure that from our Canvas you click on the worksheet and make a copy. It looks like this. That's going to be what you want to keep handy while we're going through this video or while you're going through the slides, so that you can go ahead and get that material and that information as you're being exposed to it in the video or in the slides. So let's check out the slides and let's get going. All right, so this is our geologic time scale. And time, when we're talking about the age of the Earth, is called deep time because it's so big, it's something that we can't even really conceive of. It's too big for us to think about in our minds. So we have to try other ways to understand it. And it's important to understand the age of the Earth so that we can understand her history. And that's really what we're going for, is to understand about the Earth and all the things that have happened in the history of the Earth, so that we can understand about how she's put together and about how all of her processes work to still make her a dynamic force 4.5 billion years after her creation. So it is estimated that the Earth, along with the solar system, was created about 4.6 billion years ago. Created, we're still kind of figuring that out. There's lots of theories like the Big Bang Theory and string theory, but right now we're looking up and we're saying either way, regardless of how she got here, we know that she's about 4.6 billion years old, which is the same age as the solar system. And we look at the scales of time in the Earth's history in a few different ways. We break it down into eons, which is the largest segment of time, and then eras, and then periods, and then the smallest segment of geologic time is called an epoch. And we can see here eons, eras, periods, and then epochs. And those are all based on millions of years. So there are two real ways to look at the passage of time. There is relative time, which is to know the order of events, but not necessarily the specific dates. So like we know that the Civil War happened before World War II, right? We don't know exactly maybe what those dates are off the top of our heads, but we know that the Civil War happened before World War II. We know that you were born after I was because I'm older than you. So our relative age is that I'm older than you. You were born after me, right? Well, in terms of geology or the Earth, we know that the bedrock in the state of Wisconsin was formed before the big last set of glaciers came in the last ice age. And so that's how we talk about relative time. We just say something is older or something is younger or this happened before that. There's also absolute time, and absolute time tells us the exact age of something based on the dates, right? So like the Civil War was from 1861 to 1865. World War II, though, was from 1939 to 1945. And the glaciers left the state of Wisconsin about 11,000 years ago. So that's absolute time. We have exact dates on those, or pretty close to exact dates in geologic time. And so we can say that's called absolute age. So here's another example of the difference between relative and absolute age. So like we don't know the exact ages of all of these people, but we know their relative age in relationship or relative to each other. So we can list them from youngest to oldest. We have a baby, we have a teenager, and we have an adult. And we know that they are listed from youngest to oldest just like this, right? The baby's younger than the teenager's younger than the adult. So we like to use relative time to help us find the ages of rocks. And so we call this method the law of superposition. And you're going to hear about the law of superposition. That's something you really need to make sure you learn. But the law of superposition just says that undisturbed sedimentary rocks, so rocks that haven't been eroded or haven't had earthquake uplift or anything, that those oldest rock layers are at the bottom and the youngest are at the top. So if you have a bunch of rock layers like in this picture, we can say, based on the law of superposition, that these old rocks are older than these youngest rocks, right? And we know that rock layer A is older than rock layer C. And rock layer C is older than rock layer H. So we also know that rock layer I is younger than rock layer F, and rock layer F is younger than rock layer B. So that's all relative age, and we're doing that using the law of superposition. Another concept in geologic time is the concept of uniformitarianism, and we actually see this in biology as well. But uniformitarianism is a theory that changes in the Earth's crust are because of processes that happened millions of years ago. So what that means is that, like, the things that we see happening today are things that happened millions of years ago. And with uniformitarianism, we can say that those things are going to continue to happen in the future. So if I saw something happening right now, like an earthquake or a volcano, and those things changed the Earth's surface, I could say, well, those things probably happened millions of years ago too, because I can see evidence of volcanoes exploding. I can see evidence of earthquakes from millions of years ago. And it stands to good reason that we'll also see those things in the future as well. And that, again, is called uniformitarianism. So things are uniform. They happen the same way over billions of years. And if they happened before, they'll happen again, and we can kind of count on that. So in uniformitarianism, we use another method of aging rocks, which is called the law of included fragments. The law of included fragments says that if fragments of one type of rock are found in another rock layer, the rock fragments must be older than the rock layer in which they are found. That may be confusing. I'm just going to tell you, I call this my chocolate chip cookie law. So the law of included fragments says that if I'm looking at a chocolate chip cookie, the chocolate chips in my cookie are older than the cookie itself. And that's got to be the fact, right? Because we had to have the chocolate chips present in order to have them in the cookie. So they've got to be older than the cookie. The cookie was baked after they were made. So the chocolate chips are older than the cookie, right? And that's just the law of included fragments. We know that, like in sedimentary rock, big chunks of rock that are part of the sediment that made those rocks, those big chunks of rock in the sediment are older than the rock itself because they were there before the rock was made. So as we're going forward, we also want to look at some things that happen in geology with regard to Earth movement and changes. So let's look at some faulted and folded layers. Layers of rock that have been faulted, cracked, right, faulted, or folded, like bent through deformation, must have been present before the actions of faulting and folding took place. So what that means is these layers here and these layers here were all laid down first, right? And then after they were laid down, that's when the bending or the folding happened. And after they were laid down, that's when the faulting or the breakage happened. So faulted and folded layers are ways that we can help age rock by looking at, oh, hey, we know that these layers were there before the faulting and folding. And so we can say that that faulting, that folding, that's younger, right, than the layers of rock. The layers of rock were there first, then they were bent, then the faulting happened. So those layers of rock are older than the faults or the folds in the rock layers. Let's look at unconformities. So unconformities are when we see some sort of a break in time. Like we can't figure out what happened. Maybe we don't know what happened. We weren't there to see it happen. But we can see a difference. So let's look at this picture. We can see these rocks here. They're all kind of a dark gray color, and they're sort of jutting up this way, right? But then on top of that, we have another layer, and it is a lighter color of rock. And notice that the layers are just straight across. An unconformity is this break right here, this line. Something happened between when these rocks were made and when these rocks were made. And it caused this set of layers to be jutted or tilted to the side, and then these layers were laid down afterward. We're not sure what happened. That's missing. That information is not with us. And so we call that an unconformity. We can see a illustration of an unconformity here too, where you have these layers here, and then there's this break in time or this unconformity, and then we have some new layers on top of that. We also can use rock correlation to help us age rock or layers of the earth. So we can look at layers that are similar to each other, and when they're exposed because of something like the Grand Canyon, like erosion or whatever, we can look at those layers and we can compare them to other layers that are similar. We might see that some of those layers are not exactly straight across, but maybe, like, for instance, this side was lifted up because of an earthquake, whereas this one was not. And so even though these layers match, we can kind of say, hey, they match, they're pretty much the same, they're probably the same age, even though they're not straight across from each other. Because after this erosion happened, something happened to maybe lift this side up. That helps us to age these layers, but it also tells us that something else happened there that maybe we don't know about yet. Also, we can see these are called outcrops. This is when we have exposed layers of rock, and we can see them. And also, I want to point out a key bed. Key beds help us to age rocks too. They are usually a result of volcanic activity. They're usually ashfall from some sort of volcanic activity, and we can date that ashfall using what's called carbon dating, and that's absolute dating. So key beds can help us age rocks too, because they allow us to age rocks based on when the last volcanic eruption happened, and they can help us determine how old the rocks are above that and just below that, right? So those are pretty cool. We also use radioactive dating to help us date rocks, and I already kind of referenced this with carbon dating, but we can use radioactive isotopes that are present in the Earth's crust to help us to age rocks. We know exactly how long it takes for radioactive materials to break down. And so knowing that information about how long it takes for radioactive materials to break down, we can use how much of it is present in an existing layer to determine how old those layers are. And radiocarbon or radioactive dating is a absolute dating method. It gives us exact dates, and that's helpful because some of these other methods, like comparing rock layers or looking at unconformities or seeing bending and folding or whatever, those are more like relative dating, like older, younger, things like that. Radiocarbon dating gives us some exact dates. There are some other dating methods we use using radioactive isotopes. Like, for instance, we can use uranium and lead, we can use rubidium and strontium, and we can use potassium and argon. And those are also dating methods that are absolute. Okay, so that's the end of your notes. If you missed anything from the video, you can go back and watch it again, pause, rewind. You can also use these slides, which are present in your Canvas assignment, to fill in the worksheet, right? Get all these filled in, and then go ahead and go over to Canvas and get it turned in. All right, thanks a lot. Have a great day.